In the past, we've talked about sample data and using the sample data to make inferences. In other words, we're going to estimate or we're going to make predictions about the population. Well, now we're going to talk about this estimation process in greater detail, and the process of estimation includes the following steps. Number one, we define the population carefully, then we define the relevant population parameter, for example, the average of annual salaries of a hospital's clinical staff or the CEO's salaries. Then we select the sampling method. For example, we might use simple random sampling. Then we collect the sample data. Then we apply an appropriate estimator, in other words a formula, to the sample data to calculate the estimate of the population parameter in which we're interested. And here are our objectives. You have those in your slides as well. And what we've done so far is to calculate point estimates. And a point estimate is a single value or point derived from a sample, and it's used to estimate a population value. For example, we used x bar to estimate the population parameter mu. So x bar is our sample mean, and mu is the population mean. And so on down the line for the standard deviation, variance, and so on. So with the point estimate, we're saying I don't know what the value of the population parameter is, but the value of the sample statistic is my best guess. And the definition is a confidence interval estimate is a range of values constructed from sample data so that the population parameter is likely to occur within that range at a specified probability. And that specified probability is called the level of confidence. So we have our point estimate, which again, that's our best guess of the population parameter. And when we use interval estimation, we're saying I don't know the exact value of the population parameter, but I'm 95% confident, or some other value, I'm 95% confident that the value falls between the following two numbers. The margin of error is the maximum expected difference, or the error between the sample mean and the true population mean, depending on the level of confidence. We'll look at two different similar situations to compute a confidence interval. One, when we know the population parameter of the standard deviation, and one when we don't. But first, we'll talk about the factors affecting the confidence interval estimates. We use the sample size and the standard deviation in the calculation to determine the range of the confidence interval estimate. And we have the instructions on the screen. The width of the confidence interval is determined by the sample size, n, the variability in the population, which is the sigma, population standard deviation, usually estimated by the S, which is the sample standard deviation, and then our desired level of confidence. So let's take a look at the formula for estimating the confidence interval for a mean when we know the population standard deviation, which we usually don't know. And you can find more about this on page 301 of your text. The formula for the confidence interval for population mean when we know the population standard deviation is x bar plus and minus z times the population standard deviation divided by the square root of n. And this may seem a little confusing at first, but as we break it down, I think you'll find it a little bit clearer. The formula is the point estimate of x bar. So we've determined what the best guess of the population mean is, and that's the x bar value. And then what we're doing is we're adding this formula to that x bar, and we're also subtracting this formula from the x bar. So let's say this value, let's say our x bar is equal to 5, and this value turns out to be 2. So we'll have the x bar minus this value of 2. So 5 minus 2 would give us a point over here of 3. And then we have the x bar, which is 5. And then if we did our adding of this point, then we would be adding 2 to the 5. So we would have a point of our left limit of 3, our mean of 5 and our positive limit, or our right limit, is 7. And that would be our confidence interval. But we're going to get into it a little bit further. The width of the interval is determined by the level of confidence and the size of the standard error of the mean. And the standard error is affected by two values, the standard deviation and the number of observations in the sample. Well, we as researchers choose a level of confidence, which determines the z-value. And usually people are using 95% and 99%, or let's say traditionally 95 and 99% are two different types of confidence intervals that are frequently used. Well, how can we tell that the standard error is affected by the standard deviation and the number of observations in the sample? Well, because one is the numerator, and the other is part of the denominator. So let's take a look at this formula a little bit closer. If we break apart our formula here, which is our confidence interval formula, we have x bar plus n minus z times the population standard deviation divided by the square root of n. Well, the standard deviation divided by the square root of n is equal to our standard error of the mean. And then when we add in the z-score times the standard error, we get our margin of error, and then when we add in the point estimate, we now have our entire confidence interval formula. And the margin of error is the maximum expected difference or error between the sample mean and the true population mean, depending on the level of confidence. And we use our choice of our comfortable level of confidence to determine the z-value used in the margin of error calculation. If you remember back in class, we talked about if we're talking about something that's life-threatening, we might want to have a tighter confidence interval than if we were working on something that's not quite as critical. So let's take a look at a graphical depiction to better understand. In our depiction, we have the plot of a population distribution with our mean, or our mu, right here in the center. So for a 95% confidence interval, about 95% of the similarly constructed intervals will contain the parameter being estimated. So let's walk through that a little bit. So sample 1, we take a sample of size 256. It includes the population mean. So here's our confidence interval from here to here, and our mu actually is in that range. Sample size 2, or sample 2, it was also of size 256, and it also includes the population mean. So if we took our second sample and the confidence interval turned out to be, here is our left limit and our right limit, well, the mu is in that range. Now let's jump down to sample 5, also a 256N sample size. It does not contain the population mean. So we have our confidence interval. We did everything properly based on the formula here, but it doesn't contain the mean. Well, that's the risk that we take. Assume we don't know the population mean. If we select a lot, maybe several hundred samples of X observation and build confidence intervals around them, we would expect about 95% of the confidence intervals we create out of our samples to include the population mean. And that's what we get to with, as researchers, determining the level of risk. So we know that we should expect about 5% of our confidence intervals that we create, and we're doing this a number of samples, to not include the population mean. And again, if it were more critical, we would want the population mean in those confidence intervals at a greater rate. So we might choose 99% confidence intervals, in which case we would expect only about 1% of the confidence intervals to generate to not include the population mean. Also, 95% of the sample means for a specified sample size will lie within 1.96 standard deviations of the population, of the hypothesized population. So let's go ahead and do an example. And this example is, again, a confidence interval for a mean when we know the population standard deviation. The American Management Association wishes to have information on the mean income of middle managers in the retail industry. A random sample of 256 managers reveals a sample mean of $45,420. The standard deviation of this population is $2,050. The association would like answers to the following questions and decide to use a 95% level of confidence. And I've highlighted the pertinent information for you by underlining here. And the questions they want to find out are the answers to are: what is the population mean? What is the reasonable range of values for the population mean? And what do these results mean? And by now this formula should start looking familiar to you. This is the confidence interval for population mean with a population standard deviation that is known. And it's x bar plus and minus z times the standard error, or population standard deviation divided by the square root of n. In this case, we know the population mean. We know the sample mean is 45,420. Hence, our best estimate of the unknown population value is the corresponding sample statistic. We don't know the population mean. We do know the population standard deviation. So the sample mean of 45,420 is a point estimate for the unknown population mean. And the reasonable range of values is the confidence interval we're going to try to find, or we're going to find. Think about what parts of the formula we can fill out right now. The only thing we don't know is what? The z-score. So let's move on and find the z-score. Because right now we know what the population, or excuse me, what the sample mean is, we know what the population standard deviation is, and we know what n is. Remember the table on this table that's on page 764 only gives us the value for half of the distribution. When we create a confidence interval, we want both halves. So we have to take our 95% and break it in half, which comes out to 0.4750. So our z is equal to 1.96. If we go to our point of intersection of the 0.4750, we can read to the left and we get our 1.9, and then we go up to get the 0.06. So this is our first decimal place, 1.9, the 9 is the first decimal place, and the 6 is the second decimal place. So the 95% confidence interval refers to the middle 95% of the observations. Therefore, what that means is that the remaining 5% are equally divided between the two tails. So we have 5% is the equivalent of the 0.025 or 2.5% plus the 0.025 or 2.5% here. So now we have the last piece of information that we're missing, the z-score, and we can start filling in the rest of the formula. And this is just restating the scenario here. And we can go down to our formula, which should look familiar by now, and we can start plugging in our values. There's our 45,420, which is our point estimate. Also it's also known as our mean. It's our best estimate of the population mean. And then we're adding and subtracting this formula, and that's 1.96, which is our z-score, times the population standard deviation divided by the square root of n, which equals 45,420 plus and minus $251. So the confidence limits are 45,169 and 45,000.671, and that's determined by taking the point estimate, subtracting 251 from it, which gives us our lower limit, and taking our point estimate and adding the 251 to it, which gives us our upper limit. And again, this formula is considered the margin of error, everything minus the x bar. So the z times the standard error, or z times the population standard deviation divided by the square root of n, is our margin of error. So we can say with 95% confidence we estimate that the population mean is between $45,169 and $45,671. So what does this mean? Well, let's take a look. If we select many samples of the 256 managers and construct a 95% confidence interval, we could expect about 95% of those confidence intervals to contain the population mean. On the other hand, about 5% of the intervals we would expect not to contain the population mean, or the annual income, or mu. And this you should recognize from a couple of slides before. Here's our population mean, and here are each of the example samples that we have. So the 95% confidence refers to the middle 95% of the observations. Therefore, the remaining 5% are equally divided between the tails. And what's the interpretation of the confidence limits? 45,169 and 45,671. Same as what we said before. With 95% confidence, we estimate that the population mean is between $45,169 and $45,671. So what do you suppose we would do if we don't know the population standard deviation? Well, we can use the sample standard deviation to estimate the population standard deviation, and instead of using the z distribution, we use the t distribution. And the t distribution, it's similar to a z distribution, but it is there are some differences. Like the z distribution, it's a continuous distribution. Also like the z distribution, it's bell-shaped and it's symmetrical. And there is not one t distribution, though, like the z distribution, or unlike the z distribution, which only has the one distribution. The t distribution has a family of t distributions, and all t distributions have a mean of 0, but their standard deviations differ according to the sample size of n. And the t distribution is more spread out and flatter at the center than the standard normal distribution, which is what we're showing here, the difference between the two. As the sample size increases, the t distribution approaches the standard normal distribution, though. So when the n is small and we have a 95% confidence interval, you'll notice that the t distribution is spread out further than the z distribution. So again, this is an n of 5. Now, as we get larger n, though, the t distribution will start looking more and more like the z distribution. And the confidence interval is very similar for using the z distribution and the t distribution. So here's the z distribution, which is what we did before, and you should recognize this by now, the x bar plus and minus the z-score times the standard error. Well, think of it the same way. This is the margin of error. Oops. This is the margin of error, this formula here. And if we take this formula here, we're just doing the same thing. We're taking our sample mean, we're subtracting from it this formula, and we're adding to it this formula to get our upper and lower and upper control limits, respectively. So if the population standard deviation is unknown and the sample is less than or equal to 30, that's when we would want to use the t distribution. If the population standard deviation is known, or we have a sample size that's greater than 30, we can use the z distribution. So again, remember, when we get larger n, it gets closer to the z distribution, and 30 is the number that statisticians tend to agree on is acceptable to transition over to using the z distribution, because your t-distribution is close enough to the z-distribution at that point. And of course, we have an example for a confidence interval using the t-distribution. What is it that we don't know that causes us to use the t-distribution for the confidence interval? Do you remember? Well, if you don't remember, maybe you need to back up the video and check again. Okay, just kidding. If you don't we use the t-distribution for the confidence interval when we don't know the population standard deviation. And here's our example. And this is our confidence interval for the mean example using the t-distribution. A tire manufacturer wishes to investigate the tread life of its tires. A sample of 10 should be a trigger to you, especially since it's highlighted in red. A sample of 10 tires driven 50,000 miles revealed a sample mean of 0.32 inch of tread remaining with a standard deviation of 0.09 inch. Construct a 95% confidence interval for the population mean. Would it be reasonable for the manufacturer to conclude that after 50,000 miles the population mean amount of tread remaining is 0.30 inches? And in our example here, just notice that this symbol alpha here is to indicate our confidence level. And what we're given in the problem is an n of 10, an x bar of 0.32 inches, and a sample standard deviation of 0.09. And since we don't know the population standard deviation, we're going to use the t-distribution right here. So again, we're going to compute the confidence interval, and if you were to block this all off into one formula, it would be the same thing. We take the point estimate, we add this value to get the upper limit, and then we subtract this value from the point estimate to get the lower limit. Now it's just a matter of figuring out what goes in each of these places here. And when you're looking at the t-distribution formula, don't get too caught up with all of the symbols that's going on after here. It's just to help you determine what part of the table that you're using in page 765, Appendix B2, that you're going to use. But it's not too difficult to figure out. So how do we do it? Well, we go into our table, this is an excerpt from the table on page 765, and I'd encourage you to take out your book, though, and look at the book table so that you become familiar with the way that it looks, and so that you can use it when you don't have the example in front of you or the excerpt in front of you. So we move across to the desired level of confidence. What's our desired level of confidence? Well, it's 95%. That's what we're looking for. And then we choose the row with the appropriate degrees of freedom. And that you can find more about in page 310, but the degrees of freedom is n minus 1. And that is equal to 9 since our n is 10. Here's our n minus 1 in our t formula right there. You really don't have to worry about the alpha divided by 2 when you're looking in the page 765 table, because it's already broken out for you. So we're doing a two-tailed test, and we won't, because we're using actually we're doing a confidence interval, so the tails don't make a difference. And we're going to go down our confidence interval column, our 95% confidence interval column, until we get to the row where our degrees of freedom cross, which is our degrees of freedom are 9, and that gives us a 2.262 as our t value. So now we have our t value, and so we plug in our t value, and then we plug in our other values, which we already had. We already had our standard deviation, and we had our n. So now we have our t value of 2.262. We have our s value of 0.09, which was right here, our standard deviation, sample standard deviation, and then we have our 10, which is our n here. And and of course we have our 0.32, which is our x bar right here. So it's the same thing as we did before. We have our point estimate, which is our x bar, and then we're adding and subtracting the results of the formula. The results of the formula are 0.064, and that gives us a lower limit of 0.256 and an upper limit of 0.384. And we can look at this, and then we can determine that the manufacturer can be reasonably sure, or 95% confident, that the mean remaining tread depth is between 0.256 and 0.384 inches. And here are a couple of reference pages for you. And these reference pages go along with the worksheet exercise that we'll get to in just a minute. But the confidence interval estimates for the mean, and this is how we can do it using Excel and Megastat rather than having to go through the process of using your book for it. And here's our example scenario. The manager of the Inlet Square Mall near Fort Myers, Florida wants to estimate the mean amounts spent per shopping visit by customers. A sample of 20 customers reveals the amounts that they spent. Right here. And if we use the formula, we'll come out with this confidence interval here. And again, this is using the t-distribution because we only have 20 customers. If we had 40 customers, how many what distribution would we use? Yes, we could use the z-distribution. And we find that our upper and lower control limits, or endpoints as listed here, are $45.13 and $53.57. So it's reasonable that the population mean could be $50. And the value of $60 is not in the confidence interval, so we would conclude that the population mean is unlikely to be $60. So let's take a look at Megastat and Excel and see how we do it with those. As a point of reference, in the purple at the bottom of your slide, I give you the instructions on how to get to the function in order to do the analysis on these example slides. So for using straight Excel without Megastat, you go to the Data tab, Data Analysis, and then Descriptive Statistics. For Megastat, you go to Megastat, Confidence Intervals, /sample size, Confidence Interval, and then Mean. So let's get on to our exercise. As you may remember, these are the amounts that the 20 customers spent, and our manager at the Inlet Square Mall took a sample of these 20 amounts. So we're going to calculate the confidence interval of the mean using plain old Excel in the Data Analysis Tool Pack. So we click on Data on our ribbon bar, go all the way to the right and use the Data Analysis toolbar or link, and then we want to go to Descriptive Statistics. So you have to find Descriptive Statistics, click on Descriptive Statistics, click OK, and I've already got the data in there because I ran it just to make sure I was doing it right. So here what we're going to do is you can go in this by selecting that little spreadsheet looking icon, and it'll minimize the dialog box, but it'll work just as well even without doing that. So you highlight our text, and because we're using the Megastat, we're not using Megastat, but we're using the Excel without the Megastat, you can include the headers. You just have to tell Excel that you do have a label in the first row. And what we're going to do also is, instead of putting this on a new worksheet, because we have plenty of space here, we're going to just put it right here in the worksheet that we currently have, because we only have the one column of data and it's not going to be a problem. And we want to go ahead and select our confidence level for the mean, and it's by default 95%, so we can leave that in there. And let's just, for good measure, get our summary statistics as well. So we click OK, and there we have our data already put together. And while it's still highlighted, let's go back to Home on our ribbon tab, go to Format, and do an auto format column width on there. But to make this a little bit cleaner, what I've done is I've selected all of the cells, and then by holding down the Control key, I clicked on Count, and that deselected the Count cell. And now we can go in here and go to our number. This is just a little side tip that you can do. And then your decimal place is set at 2. That'll also marry up better with what we have on the... Oops, it looks like I didn't deselect this. Oh well, we'll just get rid of it this way. It'll just marry up a little bit better with what we have in the book. Now you'll notice in here that we don't have a confidence interval. We get a confidence level, which this is your margin of error. This is what the Excel gives you, is the margin of error. And if you remember, for the margin of error, what we had to do in order to create our lower limit and our upper limit is we had to add or subtract the margin of error from our mean. So let's go ahead and do that. So we have our mean, we do equals mean, and for the lower limit we're going to subtract our margin of error, and then equals mean plus our margin of error, and we get our upper limit, $45.13 and $53.57, and that's what we got in our book approach as well when we did it longhand. So now let's go ahead and do this in our Megastat. Now I gave you, there are a couple of different ways that we can do this. The easiest way to do this is to go to Megastat, Descriptive Statistics, and you'll find that your data is probably not pre-selected like mine was, but you go in there and you select your data, this time leaving out the label or the column heading, whichever you would like to call it. Go in and select confidence interval, make sure it says 95% on there. You can put the standard error of the mean in there just to see what it comes up with, and then your basic sample statistics you can put in there as well. If you wanted to, you could also include your skewness and kurtosis, which give you a better visualization of your data set also. Now we just hit OK, and with a Megastat, as usual, it has created an output tab or an output worksheet and provided all of the information there. But let's go ahead and copy it. We select it all, hit Control C, go to the other tab, back to the other tab, and let's put it right about here. And again, while it's still selected, let's do an auto format and auto column width, excuse me, and then we can, let's see, probably it's plenty of room, I guess. So now here again, let's do this and put all of these as 2 decimal places so we can compare a little bit more clearly. And again, our confidence intervals here are the same as what we calculated down here and the same as what we have in the book. And the advantage here with Megastat is it actually calculates the lower and upper limits of the confidence interval for us, not just the margin of error. I want to point out another feature in Megastat as well, but before I do that, let's go ahead and rename our output tab and just say descriptive. Let's call it descriptive CI because we use the descriptive tab in Megastat. Now let's go back to our data set here, go to add-ins, go to Megastat. Now this is what's actually listed on your slide, and I list it there because you have more options in here when you're using this approach. So you go to Megastat, go down to confidence intervals / sample size, and ensure that you've got the confidence interval mean selected. So go up here to the top, and that's probably already selected by default. Now the difference here is that you have to input the mean. So we have the mean already, so let's go ahead and just select the mean from our data or our output from before. You also have to put in your standard deviation. So we'll put in our sample standard deviation, and then we put in our n, which is 20, and we do our confidence interval. Now here though, you get the option of choosing the Z distribution or the T distribution. So it's kind of good if you wanted to play around with it a little bit to compare the 2 distributions and what type of confidence intervals that you get from each of the distributions, or each of the distributions based on the number of samples, the observations that you have. So you can click the preview if you want here, or you can just hit the OK button. And again, we'll have our output here, and I'll copy this over just so that we can see, and we'll put it right over here. And again, we'll just for make ease of viewing, we'll auto column fit it, and we can just drop that down there like that. And we'll take all of these. Let's see if I can undo the N this time. I'll try it, see what happens. Go to number, 2 decimal places, click OK. Nope, didn't do it. So we'll just do it this way. And what is our upper and lower confidence level? Same thing as we got in each of the other instances as well. So there are 3 different ways to get it, 2 of which use Megastat, 1 of which uses the Excel data analysis tool pack. Again, here are the values that come from the data analysis tool pack. And remember, with Excel you only get the margin of error that you will have to add and subtract to the mean. And in this example here, I only give you the second method that I used in order to get the confidence interval. You can go into the descriptive statistics of Megastat and get the confidence interval as well. So let's review a little bit. When we're working with confidence intervals, the sample size is an important variable, and in practice, in real world environment, we choose the sample size, and it's based on the level of confidence that we desire, the margin of error that the researcher is going to tolerate, and the variation in the population being studied. So what if we don't know the population standard deviation? Well, we conduct a pilot study. There are different methods you can use, but you can do a pilot study where we do a small study based on a small sample of the population, determine the sample standard deviation, and use it as an estimate of sigma, or the population standard deviation. We can use a comparable study. So if somebody else has done a similar study before, we can use their sample standard deviation as an estimate of sigma. Or we can use a range-based approach. And in this case, you have to have the largest and smallest values in the population, or an estimate of their values. And what we do is we take using the empirical rule. Remember that nearly all, or about 99.7% of observations fall within the +3 and -3 standard deviations, or of the mean. In other words, a total of 6 standard deviations. And so we take the distance between the largest and smallest values is 6 standard deviations. So that we say is almost everything is in that range. So what we can do is we can estimate that 1 standard deviation, or S, our sample standard deviation, will be equal to 1/6 of the range of the observations. So we talked about ensuring that we have the appropriate sample size. And how do we get the sample size? Well, we simply take our margin of error formula and we convert it so that we solve for n. And as you can see on our slide, we're just taking algebra and we're doing a few different functions within algebra to isolate the n value, and we get n is equal to z times the population standard deviation over e squared, and e is the maximum allowable error. So let's try it, and you can find out more about this on page 318 of your book. In this case, we have a sample size determination for a variable example, and a student in public administration wants to determine the mean amount members of city councils in large cities earn per month as remuneration for being a council member. The error in estimating the mean is to be less than $100 with a 95% level of confidence. The student found a report by the Department of Labor that estimated the standard deviation to be $1,000. What is the required sample size? So we're given in the problem E, which is the maximum allowable error of $100. We're given the value of Z, which is a 95% level of confidence, which we know is 1.96 because we found that in the book in the previous example. And the estimate of the standard deviation is $1,000. And here are our instructions for getting the answer in Megastat. And you'll notice this is taking us to our confidence interval / sample size. You won't be able to do this one from the descriptives point. So let's give it a shot. We're back in Excel. So let's go to our add-ins, go to Megastat, following our purple instructions on our slide, go down to confidence interval / sample size. And here we're going to go to sample size mean. And here our E value is what? Our E value is provided as 100. And our standard deviation, if you look back at our slide, is 1,000. Our confidence interval is 95. And when we click OK, we get a sample size mean, and our sample size is 385. Going back to our slide, you'll see that the manual calculation came out to the same thing. This concludes the portion on confidence intervals, and let's move on now to one sample tests of hypothesis. And as I've done before, I've left the chapter note in here on the slide so that you know which chapter we're moving on to help you find some of the pages. A confidence interval is a range of values within which we expect the population parameter to fall. In this chapter, instead of creating a range of values for the population parameter, we use a process to test the validity of a statement about the population parameter, and we call it a hypothesis test. So what exactly is a hypothesis test? Well, first of all, what's a hypothesis? Well, let's see. A hypothesis is a statement or conjecture, speculation, inference made about a population of interest developed for the purpose of testing. And examples, hypotheses made about a population parameter are: the average age of U.S. graduate students in anesthesia nursing is 31 years old. 80% of all diabetics in the Baptist health system have had their annual eye exam, and that's another hypothesis test. Another hypothesis. So what's the hypothesis test then? Well, we use the null and alternate hypothesis in hypothesis testing. And hypothesis testing is a procedure based on sample evidence and probability theory to determine whether the hypothesis is a reasonable statement. So what we're doing is we're saying, hey, let's take a look at this, and let's say, is it reasonable for this event to occur just randomly, or is something going on here? And when we say the null hypothesis, we're talking about a statement about the value of a population parameter developed for the purpose of testing. The statement is assumed to be true unless sufficient evidence from sample data show that it's false. And then you have an alternate hypothesis statement that is accepted if the sample data provide sufficient evidence that the null hypothesis is false. And here are the 5 steps that our book goes through: state the null and alternate hypotheses. And step 2, select a level of significance. Step 3, identify the test statistics. Step 4, formulate a decision rule. Step 5, take a sample, arrive at a decision, and that decision is either we do not reject or we reject the null hypothesis. And some will argue that you don't accept the alternate hypothesis, but I would caveat it to say that you accept that the alternate hypothesis is tenable, or it is still possible. In other words, we haven't ruled it out. But most statisticians prefer that you just say we do not reject or we reject the null hypothesis and don't even refer to the alternate hypothesis. So it may help to think about the null hypothesis as the hypothesis that we want to nullify. The H stands for hypothesis, and the 0 or the sub-zero implies that there's no difference. In other words, we assume that nothing is going on. Another way to look at the steps that may make it easier to understand, and we'll talk more about this later, is step 1, you assume that nothing is going on. And then step 2 is, what do you expect to get if something is going on? And that's essentially, that's your alternate hypothesis. Assume nothing is going on is your null hypothesis. And then step 3, how much risk of rejecting the true null hypothesis, in other words, a type 1 error, which we'll talk about, are you willing to accept? And that's where it deviates a little bit from the 5-step plan that our book provides you. And then step 4, my way of looking at it is, what do you actually get in your one little sample that you took? And then in step 5 we say, well, how likely was it that you got what you got? And then based on how likely it is, if it's very unlikely, we call baloney on the assumption that nothing's going on. In other words, we call baloney on our null hypothesis that nothing is going on. And we'll talk about it a little bit more as we go on. But there's some things you want to make note of about the null and the alternate hypotheses. So H sub 0 is your null hypothesis. H sub A, and our Lind book calls it H sub 1, is an alternate hypothesis. So you may see either one of these notations, H sub A and H sub 1. H sub 1 is generally used because you may have something where you have multiple alternate hypotheses. H sub 0 and H sub 1, so the null hypothesis and the alternate hypothesis, are mutually exclusive and collectively exhaustive. So what does that mean? Well, mutually exclusive means that the occurrence of one event means that none of the other events can occur at the same time. And what does collectively exhaustive mean? Well, it means that together they encompass the entire range of outcomes. Whenever we're doing a null hypothesis testing, the null hypothesis is always presumed to be true, and the alternate hypothesis, H sub A or H sub 1, has the burden of proof, so to speak. And we reject the null hypothesis, or we fail to reject the null hypothesis. And again, this is what most statisticians go by, is you never accept the null hypothesis. When you're doing your null hypothesis testing, equality is always part of the null hypothesis. So if you use an equal statement, or a greater than or equal, or less than or equal, that always is associated with the null hypothesis. Just remember, the equality goes with the null hypothesis. So if we conclude that we do not reject, or we fail to reject the null hypothesis, it doesn't necessarily mean that the null hypothesis is true. It only suggests that there is not enough evidence, or not sufficient evidence, to reject the null. Rejecting the null hypothesis then suggests that the alternate hypothesis may be true. To prove without a doubt that the null hypothesis is true, we would need the entire population's worth of data. And you could just think about that for a little bit. But the null hypothesis always gets the equal sign because the null is the statement we are testing, and we need a specific value in our calculations to do the test. So we only turn to the alternate if the null is rejected. Okay, so our choices are reject the null hypothesis or do not reject the null hypothesis. What happens if we come to the wrong conclusions? That's where we get into the type 1 and type 2 errors. Type 1 and type 2 errors can seem to be a little bit confusing, so I encourage you to take some time going over this portion of the video and maybe review it again at a later point in time. But type 1 error is when we reject the null hypothesis when it's actually true. So we say the null hypothesis is not true, but in reality it is true. And type 2 error is when we do not reject the null hypothesis and it is not true. It's kind of the not rule as one way to look at it. So we have our chart in here, and this is what the researcher sees, and this is where we look at the null hypothesis. Or this is what the researcher does, excuse me. So in this case, the researcher rejects the null hypothesis, but in reality, the null hypothesis is true. So they rejected a true null hypothesis, and therefore they got a type 1 error. And the correct answer would have been to not reject the null hypothesis. And so we have a type 1 error. Now, on another test, or another sample, the researcher does not reject the null hypothesis. But in reality, the null hypothesis is false, and that's a type 2 error. So type 1 error is defined as the probability of rejecting the null hypothesis when it's actually true, and it's denoted by the Greek letter alpha. It's also known as the significance level of a test when we use significance level. And the type 2 error is defined as the probability of failing to reject the null hypothesis when it is actually false, and this is denoted by the Greek letter capital beta. We'll discuss these again a little bit later, and there'll be a reference slide for you at the end. But let's start looking at setting up a hypothesis. In actual practice, the status quo is set up as the null hypothesis. Remember, go back to what I was saying, where the null is what you expect if nothing is going on. It's what do you expect if nothing is going on, and the alternate is what do you expect to get if something actually is going on. So what we're trying to prove is set up as the alternate hypothesis. In other words, we aren't actually going to prove it, but what we're trying to prove is the alternate hypothesis. And remember, the burden of the proof is on the alternate hypothesis. Now, when we're doing this and we get the word problem, so you're looking for keywords and you want to convert them into symbols, and we have some examples here on the table, but some keywords include improved, better than, effective as, different from, has changed. So some of the keywords give you an indication of the inequality symbol or the equality symbol that you use. So is there a difference, or has not changed, or it has changed, or is there a change? Those types of things should give you an indication of an equal sign that you use. And if you're looking at larger, smaller than, no more than, or at least, or at most, those would be indicators that you're going to be using an inequality symbol. And of course, remember that when you're dealing with the null hypothesis always gets the equality sign. Remember also that H1 and HA, H sub 1 and H sub A, are interchangeable terms. There are one-tailed tests and there are two-tailed hypothesis tests. So a one-tailed test is going to be what you're going to use when you're having an inequality symbol, and the two-tailed test is what you come up with when you have an equality symbol. The one-tailed tests are considered directional tests, more than or less than. For example, the top right diagram here depicts a left-tailed test, and that means that the null hypothesis is that the mu is some value that equates to that some mu is greater than or equal to some value that equates to a negative 1.65 z value. And then the alternate is that mu is less than some value that equates to a negative 1.65 z value. So the critical value here that we have showing, that's the cut line That's the point at which we make the determination of whether we reject or not. And in this particular case, we're going to reject if our value ends up in the region of rejection, as our graphic depicts it as. And also you can think about it as the alternate hypothesis inequality points to the rejection region. In other words, the pointy end of the greater than less than symbol will point to the region of rejection. So let's make a distinction between a test statistic and a critical value. The test statistic is a value that's determined from sample information used to determine whether to reject the null hypothesis. So we have our z, a t, an f, which we haven't gotten to, or chi-squared. And then our critical value is the dividing point between the region where the null hypothesis is rejected and the region where it is not rejected. Again, here's our rejection region, and in a two-tailed test you have two rejection regions, one over on this side and one on this side, on either side of the tails, or either tail it falls into. And we mentioned that we are testing to see if we should reject the null. Well, let's take a look at what that means. In this example, we have an alpha level of significance of 0.05, and if you remember, that equates to a negative 1.96 and a positive 1.96 value of a z-score. Because it's a two-tailed test, we divide the rejection region evenly between both tails, so they each get 2.5%, because it's a 5% level of significance, or 0.05 level of significance. And so 0.025 goes into each tail. If the test statistic, or the z-test or the t-test, falls into one of these two rejection regions over here, sorry about that, over here or over here, then we reject the null and we assume something's going on. And let's take a look at the steps in testing a hypothesis. So step one, state the null hypothesis and alternate hypotheses. And then the other way that I describe it, the null is where we're going to assume that nothing is going on. And then the alternate is, what do you expect to get if something is going on? And then in step two, we select the level of significance, or the probability of rejecting the null hypothesis. I equate that, or define that, as how much risk of a type 1 error, in other words, the probability of rejecting the null when it's true, are you willing to accept? And you can find more of this on page 335 of your text. Then we determine which statistical test to use. For example, are we going to use a one-sample t-test? Are we going to use an ANOVA? We go to step 4, which is formulate the decision criteria. We calculate the critical values for the selected alpha using the appropriate distribution. State the decision rule for when to reject the null hypothesis. And then in step 5, we evaluate the sample, we make a decision and interpret the results. We evaluate the sample statistic against the critical values, and we reject the null hypothesis and accept the alternate, or we fail to reject the null hypothesis. And then we interpret our results. And then again, the way that I explain this portion is, what do you actually get in your one little sample that you do? And then how likely was it that you got what you got? If it's very unlikely that you got what you got based on our values that we calculate, then you call baloney on the assumption that nothing is going on. Or in other words, you call baloney on the null hypothesis. And we can use the hypothesis testing to test the sample mean against the population mean. And this should look sort of familiar to you here. So to test the hypothesis that the sample is from the sample population, when the population mean is known, we use the z-test or the t-test. And the z-test, we're using the z-distribution when the sample size is large, greater than 30, or population standard deviation is known. We went over this just a little bit ago. And then the t-test, we're going to use the t-test or the t-distribution when the sample size is small, 30 or less, and we have an unknown population standard deviation. To use the z-test or t-test, the variable must be at least interval level of measurement and normally distributed. Here are a couple of examples, or a few examples, of null and alternate hypothesis where we're comparing against the population mean. And in the first example here, we have a two-tailed test, and you can tell because we're using the equal sign and not the inequality sign. And so we have the null is that the mu, or the population mean, is equal to whatever value we use, whatever we come up with. And then our alternate is that the mu is not equal to that value. And then we point out here that the subscripts are our critical values, indicate that they're the critical values. And so we're going to reject the null hypothesis if our z-score, if we're using a z-test, if our z-score is greater than our z critical value. And this vertical lines indicate that we're dealing with our absolute value of our z-score. So when we calculate it out, first thing we do is we calculate our z critical value. That's from the book. Then we do our sample z statistic based off of the data that we collected. Same thing goes if we use a t-test. It's the same thing. We take the absolute value and we're going to reject the null hypothesis if our observed t value is greater than the absolute value of our observed t value is greater than our t critical value. And here's our t test that we would use, and here's our z test that we would use based off of our sample value. So if we go back, way back to what I was saying as the example here, is that we're going to assume with the null hypothesis that nothing is going on. And then that our alternate value is that this is what we expect to get if we determine something is going on. And so now what we're going to do is we take our little sample test, we take our little bit of sample, and we calculate out our statistic, our sample statistic, and we compare it to what would happen just by chance. And so if we find that our scores are larger than or greater than or outside of the critical value in the rejection regions, we're going to say, no way, this is baloney, that there's something going on here. Let's do a quick review. But first, and there's another purpose or value in putting statistics to work for you. Calculating the test statistic. Again, remember the first thing we're going to do is we're going to assume nothing's going on. That's our null hypothesis. Then we say, well, what do we expect to get if something actually is going on? That's our alternate hypothesis. Now we have to we determine our critical value out of the book based on our significance level that we choose. But then we want to calculate out our test statistic based off of the sample data we collect. And that's the point we're at right now. Again, this is the test statistic that we're going to calculate that we compare against the critical value. So find the difference between the sample mean and the known population mean, then find the z statistic or the test statistic. So let's assume we're going to use the z-test because we have greater than 30 observations. So we would say, here's our sample mean, and we subtract from our sample mean the population mean. Then we divide that value by the population standard deviation divided by the samples, the square root of the sample size. And you'll see that the t statistic is calculated in a similar manner. The only difference is we don't have the population standard deviation. If we did, we'd use the z-score, and so we use the sample standard deviation. And here's an example that we have. In this scenario, the Jamestown Steel Company manufactures and assembles desks and other office equipment. The weekly production of the Model A325 desk at the Fredonia plant follows the normal probability distribution with a mean of 200 and a standard deviation of 16. Recently, new production methods have been introduced and new employees hired. The Vice President of Manufacturing would like to investigate whether there has been a change in the weekly production of the Model A325 desk. A sample of the last 50 weeks yields a sample mean of 203.5 desks. Use the 0.01 level of significance. Now you notice that I italicized as well as underlined the word change, and that's to give you an indication of what type of null hypothesis, inequality or equality, we're going to use. What do you think it's going to be? Since we know the population mean is 200 and the population standard deviation, which is 16, we can use the z statistic. You remember what step 1 is? Step 1 in the book answer is that we state the null hypothesis and the alternate hypotheses. So, and the alternate hypothesis. Let's change that right now. And in the way that I explain it, the null and the alternate are, we assume nothing is going on, and that is our null hypothesis. And then what do we expect to get if something actually is going on? That's our alternate hypothesis. And then in step 2, we select the level of significance, and my way of explaining that is, what's the level of risk of type 1 error, the probability of rejecting the null when it's true, are we willing to accept? In this case, it was given to us, so just make believe that we came up with 0.01 ourselves. And then we determine which statistical test to use, and I'm using the book answer here. This is the book example, so you can go back to page 342 and go through this yourself if you want to. So then we determine which statistical test to use. Well, we're going to use the one sample z-test since we know the population standard deviation, and we're testing it against the known population mean. And again, you look at this formula. It's the same formula that we had right here. Okay, so now step 4, we formulate the decision criteria. Now remember I highlighted the word change? That should have given you an indication that this is a two-tailed test, in which case we're going to use an equals sign. So we formulate the decision criteria based on the alternate. Well, actually we did that up here already. Based on the alternate hypothesis of the mu is not equal to 200, we're going to reject the null hypothesis if the absolute value of our z-test statistic, in other words the one we calculate from our sample data, is greater than our z-critical value, which we got from the book. Since alpha equals 0.01, then our z-critical value as we go through in our book we can find is 0.005. Actually, we don't need to do it in our book. I'm sorry, that you can do based on the 0.01. Since it's a two-tailed test, we're going to take the 0.01 and divide it by 2, and that's why we have z equals z sub 0.005. And the areas between the tails is 0.99. So everything in between is everything that's not the 0.01. So the 0.01 is broken in half and split to either end of the tails, or either tail end there. The rejection areas are based on 0.5 minus 0.005, which is equal to 0.4950. And we can see table B1 in our appendices to do that. And since this is a two-tailed test, getting back to the second bullet, the second bullet has us dividing the significance value by 2, giving us a z-critical value based on z.005, or a z-critical value of 2.58. And that's what you'll notice is indicated on the bottom in our distribution here. So the z-critical value is equal to 2.58. We're going to reject the null hypothesis if our sample statistic, our z statistic that we calculated from our sample data, is the absolute value, that is, of our z statistic or z score is greater than 2.5, which was the critical value that we determined from Appendix B1. So you could also state this formula here, if it makes it clearer for you, as reject the null hypothesis if the z is not between negative 2.58 and plus 2.58. So that would mean this is the not reject area, this is a rejection region, and this is a rejection region. So the shaded areas on either of the tails are the rejection region. Finally, in step 5, we make a decision and interpret the result. So we evaluate a sample. So what did we get in our one little sample? And how likely is it that you got what you got? And that's going to be based off of our significance level that we calculated. And if it's very unlikely, we're going to call baloney on the assumption that nothing is going on, or the null hypothesis. So step 5, by the book, evaluate sample, make decision, and interpret, which is helpful, but I find that adding in a little bit more clarity helps people out in understanding it a little bit. So we calculate, again, this is our z statistic or our z score based on our sample data. It's the absolute value of our z statistic, and we want to see if it's greater than the z critical value, which is what we determined from Appendix B1. I think it was B1. Yes, B1. So we stick our z formula in here, which is x bar minus mu divided by the population standard deviation divided by the square root of n, and we take the absolute value of that, and we see if that's greater than 2.58. And yes, Firefox just died. So plug in our numbers, 203.5 minus 200, and 16 divided by the square root of 50. And you should be able to do this all on your head. Just kidding. And is it greater? The result of this calculation here, the absolute value of this calculation, is 1.55. So it is not greater than 2.58. So here's where 1.55 is in our distribution. That's our computed value of z. And because 1.55 does not fall in the rejection region, we fail to reject the null hypothesis. We conclude that the population mean is not significantly different from 200. So we would report to the Vice President of Manufacturing that the sample evidence does not show that the production rate at the plant has changed from 200 per week. Let's compare the rejection areas of the 1- and 2-tailed tests. So in a 2-tailed test, you have 2 rejection regions, and we've split the 0.00 or the 0.01 into 2 parts, 0.005, 0.005. If we only did this as a 1-tailed test, then we'd have the entire rejection region on 1 tail only, and it would be the full 0.01 would be the rejection area. Again, the same thing though, 0.99 99% is not rejected. 99% of the distribution is not rejected. Depending on whether it's a 1-tailed or 2-tailed, is whether or not you're going to have multiple regions of rejection or just one. And this could have also been over here instead. Can we conclude, because of the improved production methods, that the mean number of desks assembled in the last 50 weeks was more than 200? Well, our computed z statistic was 1.55. So it's still not in the rejection region. It's still in the do not reject region. So no, the sample evidence does not show that the mean number of desks assembled is greater than 200. And so what do we do if we don't know the population standard deviation? You guessed it, we use the t-statistic. So if we don't know the population standard deviation, we use the sample standard deviation in its place, and the t-distribution is used as the test statistic which is computed using this formula. And of course, that goes back to this slide right here, and they look identical except for we're using a z and a t, and then we're using the population standard deviation versus the sample standard deviation. And this is somewhat similar to when we're doing the confidence interval. And the next scenario that we have is about insurance. The McFarland Insurance Company Claims Department reports the mean cost to process a claim is $60. An industry comparison shows that this amount to be larger than most other insurance companies, so the company instituted cost-cutting measures. To evaluate the effect of the cost-cutting measures, the supervisor of the claims department selected a random sample of 26 claims processed last month. The sample information is reported below. At the 0.01 significance level, is it reasonable to conclude the mean cost to process a claim is now less than $60? And again, you'll notice that I highlighted now less than $60 to kind of give you an indication of what you should be looking for to determine, are we going to use an equality sign or an inequality sign? So what test statistic should we use? Well, considering we already did the population and the z-test, and it says t-test at the top of the slide, you could infer that that's probably what you want to do, or speculate. But we don't know the population standard deviation, and we have fewer than 30 observations. So we use the t-statistic. What's step one? Step one is that we state the null and the alternate hypotheses. In other words, we assume nothing is going on in the null hypothesis, and then we say, what do we expect to get if something is going on, and that's our alternate hypothesis. Then step two, select the level of significance, and the level of significance is the level of risk of type 1 error. And remember, type 1 error is probability of rejecting the null when it's true. Are we willing to accept? And guess what? We picked 0.01 again as our level of significance, mainly because it's in the problem that way. Then we determine which statistical test to use. Well, we already talked about that. We have one sample test because it's the n is less than 30, and we don't know the population standard deviation. And step 4, we're going to formulate the decision criteria. And remember, the point of the alternate hypothesis inequality symbol points in the direction of the rejection area. And remember too that the equality goes with the null hypothesis. And I skipped over that here. The null hypothesis is that the mu, or the population mean, is greater than or equal to $60. The mean cost to process a claim is greater than or equal to $60. And our alternate is that the mu, or the population mean cost to process a claim, is less than $60. And we go to formulate our decision criteria. And again, this is where we come up with the critical value, and the critical value is what we determine based off of our significance level that we chose, our chosen significance level, and in this case the book authors chose it for us because I want to stick close to the book answers. And we have the significance level of 0.01, and it's a single tail noted by the greater than or less than symbols. Remember, the point of the alternate hypothesis inequality symbol points in the direction of the rejection region, so we could draw it out over here. Getting a little ahead of ourselves though. So we're going to reject the null hypothesis if the t value, or the absolute value of t is, or excuse me, the t value is less than the t critical value, or the t value is less than t sub alpha comma n minus 1. Since alpha equals 0.01 in the left tail, the t critical value is a negative, and then we get the where the degrees of freedom is n minus 1, and the area above the rejection region is 0.99. So all of this here that's unshaded, or shaded in gray, unstriped, let's say, is 0.99 or 99%. The rejection area is based on the critical value in the table B2, and that's in the back of your book also. The alpha level is 0.01, degrees of freedom is 25. We go to our back of our book and we find that the T critical value is 2.45, or in this case it's a negative 2.45 because we're looking at a less than situation. So we're going to reject the null hypothesis if the T test statistic that we calculate using our sample data is less than the T critical value of negative 2.485. So again, we're going to reject the null hypothesis if our T statistic based on the calculation of using our sample data is less than the T critical value that we calculated using our significance level, the significance level that we chose, and the appendix in the back of our book. Okay, so back of the book. And this is just explaining how you can go about doing it. Again, I encourage you to open up the back of your book so that you can see what it looks like in your book rather than just this snippet that's shown here. So we go to one tail column. We're looking at a one-tailed test over here, and we want 0.01. Now where it can get confusing is if you start looking at the confidence intervals up here. We don't want to do that. We want to look at the one-tailed test, and you're going to look at 0.01. Obviously, we only have specific amounts in here, so it goes from 0.01 to 0.005. We don't have a 0.008 in there. So there are limitations of using the table. So we take the one-tailed test, and the 0.01 is our alpha significance level. We go to our degrees of freedom, which is 25, which is our n-1 row, and we go where they intersect and we get 2.45. And again, because we're using a less than here, our rejection area is going to be a negative. It'll be a negative critical value, or that's our cut value, our cut line in there. And then finally, we go to step 5, and step 5 is make a decision and interpret the result. Or, in other words, what do you actually get in your one little sample? How likely is it that you got what you got? If it's very unlikely, call baloney on the assumption that nothing is going on. In other words, call baloney on the null hypothesis. And it appears that something is going on. So because when we calculated out our T sample statistic using our T formula, remember, the T critical is over here, and that's what we calculate based on our significance level from the back of our book. We calculate our T sample statistic, and we get a negative 1.818, and that puts us right in here. And this is the do not reject region. Here is the region of rejection. Because negative 1.818 does not fall in the rejection region, the null hypothesis is not rejected at the 0.01 significance level. We have not demonstrated that the cost-cutting measures reduce the mean cost per claim to less than $60. The difference of $3.58 between the sample mean and the population mean could just be due to sampling error. Here are some reference pages for you that you can print out, and this is just referring to the type 1 and type 2 errors again that we've been talking about. And type 1 error is the probability of rejecting the null hypothesis when it's actually true, and a type 2 error is when it's the probability of accepting a null hypothesis when it's actually false, and we put the accepting in quotes because we don't accept the null hypothesis. Here again is the chart that's similar to the one we saw before with the type 1 and type 2 errors. I encourage you might want to print these out. And there's another way to do the hypothesis testing using the p-value, and that's gained a lot more favor over the years as the computing power has improved, because the computer can do all of the calculations for us. And it's called the p-value in hypothesis testing. It's the p-value is the probability of observing a sample value as extreme as or more extreme than the value observed given that the null hypothesis is true, and it's tied to the test statistic from the sample. And in testing the hypothesis, we can also compare the p-value to the significance level, and then we come up with a decision rule using the p-value. And that is, we reject the null hypothesis if the p-value is less than the significance level, or our alpha level. If you look in your syllabus, there is a link to Keith Bauer's statistics. I encourage you to go there and look up his p-value discussion. And in it, he has a relatively easy way to remember how to use the p-value. And the decision rule using the p-value in Keith Bauer's approach is to say, if the p-value is low, the null must go. If the p-value is low, the null must go. In other words, if the p-value is less than the significance level, we reject the null. So just remember, if the p is low, the null must go. And you can sing that if you'd like. Let's take a quick look at an example. So in our last problem, we had the hypothesis and decision rules set up as the null hypothesis was that the mu was greater than or equal to $60, and that the alternate hypothesis was that the mu was less than $60. And we're going to reject it if the t value is less than the negative t critical value, where the t statistic, the test statistic, was negative 1.818, and the t critical value was negative 1.708 at an alpha level of 0.05. So we can also use the p, where we reject the null hypothesis if the p is less than the significance value, or the p is low, the null must go. And choosing option A using the back of our book, we aren't able to calculate an exact p-value from the table because we don't have every value in the table. So the best is that somewhere the p-value is somewhere between 0.025 and 0.050. With Megastat, though, we can go in and calculate an exact p-value, and that comes out to 0.0405. Well, how do we do that? Well, let's go back to our spreadsheet. Go back to Megastat. Doesn't matter what's up on which tab you're in. Then we go down to the probability, mouse over to probability, and then mouse down to t distribution. Click on t distribution because we are trying to calculate a t distribution, and make sure that you put in negative 1.818. And we want to select calculate the p given the t, because we know the t statistic. We calculated out the t statistic, remember, in our last portion. And then we go in and we put in our degrees of freedom of 25. And because we're looking for a left tail distribution, we want to shade the lower portion. So we select lower, and make sure it's not on upper. And you can do this with if you want. You can do patterned, transparent. We'll do pattern just for fun. And you can show the access points. If you want to overlay a normal curve on there, you can. And you can show your center line. So we hit OK. And there we have our distribution showing the p-value for us. And, well, let's stay here. Our p-value is 0.0405. Go back here. 0.0405 is less than our significance level of 0.05. So if the p is low, the null must go. We reject the null hypothesis at the 0.05 significance level. We accept the alternate hypothesis that the mean cost per claim is less than $60 after the cost cutting measures were implemented. One final note of clarification on this. We changed, if you remember our previous example, we actually used a significance level of 0.01 in our example. We did not use here 0.01 in our previous example. So in using the p-value test, we switched it over to 0.05. That way we could see that the p is low and the null must go, so we rejected it. Just the point of clarification there, so you don't get confused. This is a different significance level from what we used earlier. So in this case, we reject the null hypothesis that at the 0.05 significance level, and we accept the alternate hypothesis that the mean cost per claim is less than $60 after the cost-cutting measures were implemented. If the null hypothesis were true and the sample mean and the population mean were from the same population, we would see a difference in mean cost per claim as large as $3.58 in only 4 out of 100 times. Now, one of the things to note here is you notice that when we ran this at 0.01 level of significance, we found that we do not reject the null hypothesis. But if we run it at 0.05 level of significance, we do reject. So the point here is that you need to make a decision beforehand, because ethically speaking, running the analysis a second time and changing the significance level because you didn't get the results, say, that you wanted, or you didn't reject the null hypothesis, that's shaky science at best. And you do not want to do that. So you always make your determination beforehand. We changed it just for the sake of this example. And so let's take a quick take a look at the comparison between a test statistic and the p-value approaches to testing. In our test statistic approach, it depends on the directionality of the hypothesis, but what we do is we take the absolute value of the test statistic and compare it to the critical value. If the absolute value of the test statistic is greater than the critical value, then we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. If the test statistic is greater than the critical value, we reject. Otherwise, we fail to reject the null hypothesis. If the test statistic is negative or less than the negative critical value, then we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. So that's if we're using a two-tailed test. So in other words, if the two different ways of looking at it. This is one way to look at the two-tailed test. And the absolute value of the test statistic is greater than the critical value, then we're going to reject. Otherwise, we fail to reject. Otherwise, if we break each tail separately, we'd have to be in the rejection region on the right or the rejection region on the left in order to reject the null hypothesis. In the p-value approach, all we do is say if the p is low, then null must go. If the p-value is less than the alpha significance level, then we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. And we can look at this graphically as well. So here's the p-value approach compared to the test statistic approach. So in the test statistic approach, where we're comparing our statistical test of z to a z critical value, and it could be a t-test as well, but we're comparing our test statistic against our critical value. This just happens to be a z distribution. We are seeing, are we in the rejection region or not? And in the p-value approach, what we do is we're comparing the p-value to a significance level. And so we say, well, if the p-value is low, then we reject the null hypothesis. If the p is low, the null must go. So for the test statistic approach, what do? We calculate the critical value, which is really just the z or t value of our chosen significance level. And then we compare the test statistic of our sample observation against the critical value. If our test statistic is outside the critical region, in other words, it's in the rejection region, outside the critical value in the rejection region, we reject the null hypothesis. For the p-value approach, we calculate the z or t test statistic value. That's the one that's based off of our sample data. And then we calculate the probability of finding that z or t test value or a value that is more extreme. And that's our p-value. And we then compare that p-value to the significance level we have chosen a priori, which means we chose that before we did our research, before we actually did our analysis, before we actually took our sample, so that we're ethically clear. And then if the p-value is low, the null must go. We reject the null hypothesis.